2021 question number 3. This is a really good question. Really enjoy this one. So we have this acid, the pronunciation of which I'm not 100% sure of. Let's call it levulinic acid. Apologies if that's not correct. Tick the names of the functional groups present in the acid in the answer booklet. So this should be pretty straightforward. We've got this functional group here, which is clearly a ketone. And then we've got this functional group here, which is clearly a carboxylic acid. As far as functional group identification goes, that's going to be a relatively easy one. Usually it'll be something much harder, like identifying amides, I think is the one that trips most people up, because they mistake it for either a ketone or an amine. Anyway, give the molecular formula. So we've got 1, 2, 3, 4, 5 carbons, C5, 1, 2, 3 hydrogens here, 4, 5, 6, 7, 8, H8, and there are 3 oxygens. Again, a relatively easy molecular formula one. You know, I think there was one year where they asked you to work out the molecular formula of beta carotene or some similar compound, and there was like 50 carbons in it, or maybe 25 carbons, I can't remember exactly. But certainly, as far as molecular formulas go, that's going to be relatively easy. Then we have this synthetic route from fructose to our final acid. And you're asked to circle in the answer booklet the 2 atoms in the linear form of fructose that make the cyclic form. Alright, great question. I really like these sugar cyclizations. So we've got to go from this to this. Okay, now if you are not familiar with the way that sugars interconvert between linear forms and cyclic forms, this can be quite tricky. So let me think if there's a way that I can, if you're not aware what's going to be happening, how you can work it out. So I think the only way you'd be able to do it is you'd have to realise that this carbon here has not got any oxygen bonded to it, and this carbon here has not got any oxygen bonded to it. So these 2 carbons would have to correspond to this carbon and this carbon. Oh, I'll show you over here. Would correspond to this carbon and this carbon. So let me just put that on. That carbon there and that carbon there are going to have to be that carbon and that carbon, which means then that my ring of 1, 2, 3, 4 carbons is going to be 1, 2, 3, 4, and then the oxygen. Now you might want to count and go 1, 2, 3, 4, 5. That's obviously not going to work, right? It's going to have to be 1, 2, 3, 4, and then this one here. So that oxygen is going to be that oxygen. And what happens is this oxygen here comes round and attacks there to form the ring, which means that this oxygen here is this one here. Okay, so it's really important that you can sort of identify which atoms in here are which atoms in here. So the ones that are going to bond together are going to be this one and this one. And then that's going to give me 1, 2, 3, 4, 5, which correspond to, start at the oxygen, 1, 2, 3, 4, 5. Is that correct? Yeah, I think that's correct. Yeah, because the 5 is bonded to this oxygen, and I said this oxygen was the carbonyl oxygen. Yep. Okay, so again, it's just about sort of counting carbons, keeping track of carbons and other atoms between different forms. Okay, then we are given this elimination, so a simple elimination of water, dehydration, very common reaction, probably should be familiar with this, to go from an alcohol to an alkene. And it asks you to draw the structure of alkene A, which can isomerise to form B. Okay, so then we're given, so this is the dehydration, and then this is the isomerization. So to go from a, this would be an enol to a ketone. All right, so this comes up seems to be almost every year we're getting this keto-enol isomerization. Here they haven't made too much of a big deal out of it, but it should be quite clear what's happening, right? So this hydrogen here ends up down here. So because here there's only one hydrogen, whereas now here there's two hydrogens. So by moving the double bond up to here, the hydrogen comes down here. So anyway, it says draw alkene A, which can interconvert to form B. So that means that this is going to turn into an alcohol, and then the double bond, rather than being there, is just going to be there. Okay, and then the hydrogen that was here is the one that ends up over here. So I feel like that is relatively straightforward. Like that, and then it doesn't matter. There's nothing about cis or trans here, so you can draw the cis or you can draw the trans. I feel like if they wanted to, obviously they have to decide how many marks and how difficult each question needs to be. That's probably one avenue they could have gone down. Perhaps start bringing in some geometric isomers, but not on this occasion. Then it says draw the structure of the other tri-substituted alkenes that could also be formed. So up here we do the dehydration to form A. So we've gone from our cyclic form of fructose to this alkene, but it's saying there are other alkenes that could have been formed. Obviously, okay, because what I've done is I've lost this alcohol group, but I've got 1, 2, 3, 4 other alcohol groups that I also could have lost. Okay, so let's have a think about. I'm going to go at this in a sort of, rather than just like wing it, let me be a little bit more systematic about it. Well, that's not correct at all. Like that. Okay, so to form this one, we got rid of this alcohol here, and then form the double bond there. Okay, so let's now go through and consider. So that one's done. Okay, let's now go through and consider the other ones. Now, if I take this one off, I'm just going to show you this as a non or a counter example. Let me draw properly. If I take this one off, then I get, I can't do it, because this carbon here is bonded to 1, 2, 3, 4 other things. There's no hydrogen for me to lose. Okay, you remember here, look, that in order to do this elimination, I have to have a hydrogen bonded to the adjacent carbon. So there's no way for me to do that. So I can't have then like a double bond here. All right, it's not going to work. Okay, so that one doesn't work. We can't do it with that one. Okay, so let's now think about this one. All right, now for the same reason, I can't form the double bond here because this can't lose a hydrogen, but I have got a hydrogen here. Okay, so that's going to give me that stays the same. That stays the same. I've still got my alcohol group there, but now I've lost that alcohol. So I lose the alcohol here and the hydrogen here, and I make that. Okay? Now, that's that one done. But I could do the same for this one. So I lose this alcohol and this hydrogen. I make the double bond in the same place, but now the alcohol is down here. So I'm also going to get this one. Alkene in the same place, but this alcohol here. Okay? And then we're not quite done because there's a hydrogen here as well, which means I can lose this alcohol and this hydrogen and form the double bond here. So I'm also going to have that one there, and then everything else the same. Okay, and then it's important to realise that I can't lose this alcohol. Can't lose. All right, so sorry. Let me just think about this for a second. So I was thinking if I could lose this alcohol and this hydrogen, that could work. So let me draw that out. So I've still got that bit. I've lost this alcohol. Now I've got the double bond there. And I've got that. So that could happen, but that's not one of the answers. And that's because you are told it has to be a tri-substituted alkene. But here, this alkene has got 1, 2, 3, 4 things, and none of them are hydrogen. Okay, so if I double check all of these, I've got 1 hydrogen, so I've got 1 substitution, 2 substitutions, 3 substitutions. Okay, here I've only got 1 hydrogen, here I've only got 1 hydrogen. So that's okay, that's okay, that's okay, that's not okay. And likewise, I could have lost this alcohol here. All right, let me just run out of space here. If I were to lose that one, so I lose this alcohol and this hydrogen, I would have formed OH, 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 OH. I would have formed this. Okay. So by losing the alcohol at this end of the bond and the hydrogen at this end of the bond, then I form this one, and that one obviously is also not okay because that's not tri-substituted, because I've got hydrogen here and I've got hydrogen here. It's only di-substituted. So those are my 3 possible tri-substituted alkenes. I feel like I made that a little bit more complicated than it needed to be. You might need to rewatch that one if it's not completely clear. But anyway, let's carry on. So then we are told that compound B can be converted into compound E via the elimination of 2 more molecules of water. So via C and D. So obviously what happens here is it should be clear that nothing changes over here. Nothing changes over here. So what I'm doing is the 2 water molecules I'm losing are this alcohol and this hydrogen, and then this alcohol and this hydrogen. And it doesn't matter. So I could either do this one first and then this one, or I do this one first and then I do this one. But either way, it doesn't matter. And essentially what I'm going to be doing is I'm going to be sort of, not this, what I'm doing is when I went through here, you know, I did this side first, and then so I did this side first, and then I did this side. So it's the same thing. So, having worked out the tri-substituted alkenes, this should be quite straightforward to do. Keep missing out that carbon. Definitely don't want to do that. Alright, so let's lose this side first. So I lose that one, and I've still got my OH there, and then I've got that. And then I lose this side to make this up here. Or I could have lost it from the other side. So it would be like that, and then I've still got that one. Okay, but it doesn't matter which way you do it round, and that's why you're given one big box for C and D rather than a box for C and a box for D, because C and D could be either one. Okay, and then draw the structure of compound F. So compound E can be hydrolyzed to the acid and byproduct compound F. So let's have a look at F. Okay, at this point, I mean, in my experience, the most common byproducts in these questions I think the one that I've come across most is always carbon dioxide or something similar to carbon dioxide. So my sort of instinct at this point is to think to myself, right, well, how many carbons have I got here? I've got 1, 2, 3, 4, 5, 6. How many carbons have I got here? 1, 2, 3, 4, 5. All right, this is going to have carbon in it, okay? And it's going to have 1 carbon in it. And then I've got the IR information. So I've got this broad and then this not broad. This immediately should be C double bond O. You are these days given infrared data, so you don't need to know the common ones. I think when they did this paper back in 2021, that information wasn't given, so you were expected to know that that would be a C double bond O. And then the broad 3100 peak is just going to be a OH group in an acid. So my instinct is to go with methanoic acid, which I think is the correct answer. And we probably could work out and double check. 1, 2, 3, 4, 5, 6. This is C6, H, 1, 2, 3, 4, 5, H5O3. And then this is C5, 1, 2, 3, 4, 5, 6, 7, 8, H8, O3. And then I'm saying that this is going to be CH2O2. So if I add these two together and a water, if I add that and I add a water, do I get this? Well, I get C and C5 is C6. I get H. Oh, no, I don't get a water. No, it's not what am I saying? It's this plus H2O. That's what I'm saying. So I hydrolyze this. So I add the water to this. Do I get my two products? So C and C5 is C6, fine. H2 and H8. Oh no, I don't get it. Let me think. Okay, I had to pause it for a second then and have a little think about it, because this should have worked, and I realise I made a mistake over here, I think. So I've got 1 hydrogen, 2, 3, 4, 5, 6. So that should be 6. And then I realised the other mistake I made is that the hydrolysis, there needs to be 2 hydrolysis steps. Without going into it in too much detail, because is it easy to think why there would be 2 hydrolysis steps? I'm not going to stress myself out too much about trying to work out exactly how this reaction happens. It just seems to be sensible to me that there would be 2 hydrolysis steps, because I don't think you're going to be able to break the ring and make the acid in 1 hydrolysis step. So I think 1 hydrolysis is going to break the ring, 1 hydrolysis is going to break off your methanoic acid. But anyway, if I were to add these together, does that work? If not, I'm just going to give up. So 1 carbon and 5 carbon is going to be 6 carbons, 2 and 8 is 10, and this is 6 and 4 is 10, and then I've got my 2 and my 3, and my 3 and my 2. Yeah, okay. It works. I mean, to be honest, you had enough information at the start, right? You knew it was 1 carbon, you knew it had a carbonyl from the 1700, and you knew it had an acidic OH group from the broad 3100. So you wouldn't need to stress yourself out too much about it. I was just trying to work out just in case. So then we have this information about the catalyst. So we've got this nice ruthenium catalyst here, and we're asked to state the value of the oxidation state of the ruthenium. So the ppH3, so that is phosphorus with 3 phenyl groups. So there's going to be no charge on that ligand, because I've already got my lone pair here. Likewise with my CO, I've got my lone pair on my carbon monoxide there. So the only things to worry about are the hydrogens. Now, in order for me to have a hydrogen ligand, you're going to have a negative charge on that in order for that to have 2 electrons. So this is going to be H minus, this is going to be H minus, which means my ruthenium is going to be +2. And then my favourite type of question, isomer question, especially a stereoisomer question. So this is the stereochemistry, and then it says draw the other stereoisomers of this complex, and you're given 3 more boxes, and it says not all boxes have to be used. Excellent. And they've drawn that one in there for you. Okay, and it says tick to indicate whether the stereoisomer shown and each stereoisomer you have drawn has an enantiomer. For a pair of enantiomers, only draw one of the pair. Fantastic. Okay, so I'm not going to worry about the enantiomers first. What I'm going to do is I'm going to draw the other stereoisomers. Now, I think if you've done enough of these questions, or if you've watched any video that I've done with a similar question, the key thing with the octahedral, especially if it's an octahedral which has got 3 of the same group, is first thing you do is you go having those 3 groups all in the same plane or all on the same face. So here I've got the PPH3 groups all in the same plane. Okay, so let me think now, is there another isomer where I've still got these 3 in the same plane? So now that I've locked these 3 in, I just worry about my 2 hydrogens and my CO. And it should be fairly clear that there is one other possibility. Here, the hydrogens are not opposite to each other. So if I was to take this hydrogen and put it over here, the hydrogens would now be opposite. So let me just draw that out, and it should be clear that that is a different compound. So there's the hydrogen, and now I'm going to put this hydrogen opposite it. Okay, so hopefully you can see that those 2 are now different compounds. And what it does is by locking in your PPH3s in the same plane, it means you don't need to worry about any other combinations. Because you might start to think to yourself, oh well, what if, I've got there's a scrap paper here, you know, what if I did it, what if I drew this? What if I had, you know, you start getting into this kind of situation and thinking to yourself, oh, well, what can I do here? You know, if I put the PPH3s here, and then can I put this one here? Yeah, and then what happens over here? And it gets really complicated. But you don't need to, because if you've got these 3 all in the same plane, then it's the same as this. Don't get yourself confused. Alright? So, once these 3 are all in the same plane, I can either have the hydrogens adjacent or have the hydrogens opposite. There's no other option. Then I go ahead and I put them all on the same face. And if you don't know what I mean, or if the geometry doesn't make sense to you, you might want to get a model out. I haven't got my models with me here, so I can't show you. But if you make one yourself, it should be pretty clear what I mean. So what I'm going to do is I'm going to put them all on the same face. So P, H3, P, H3. And then it doesn't matter what I do down here. Let's just do H. Let me see. Okay. So what I mean is I've now got these on the same face. Okay. And then I think to myself, all right, well, now that these are on the same face, can I move my CO, my H, and my H in such a way as to generate a different compound, like I did up here? And it should be clear that, obviously if I swap the 2 hydrogens, nothing's going to happen. So if I swap one of the hydrogens with the CO, am I going to make a different compound? And it should be clear that no, you're not going to be able to do that. All right, because now it's symmetrical. There's a plane of symmetry along here. So any change you make is just going to produce the same compound. So we don't need that one. Then we have the slightly more tricky question of, does it have an enantiomer? Now, It's up to you. The way to do it, perhaps, is to draw out the other enantiomer. So draw out the mirror image and then decide if it's the same or not. So we can do that with this one. So I would draw the mirror image like that. And then I need to decide, are these non-superimposable? And again, this is going to be a little bit tricky for you if you're not used to doing this sort of manipulation in your head, but those are the same. And the way that I do it in my head, which admittedly I've probably had a lot more training in how to do this than you have, is I rotate it along this axis to give me, draw it out, it's going to take a little while but might be worth it, PPH3, PPH3. So I get this one comes back to here, this one goes to here, this one comes around to the front, so I get my PH3P there, I get my carbonyl there, and I get my hydrogen here, and then this hydrogen goes to the back. Okay, so now I've got that. And then you can look at these two and you think of these two the same. And what I would do then in my head is I would take it along this axis and I would rotate it 180 degrees along this axis, because what that will do is this will stay in the same place, this will stay in the same place, this will stay in the same place, this will flip down to here, this will come up to here, so no change there, and then this one will rotate around to here, this one will rotate around to here, and I get my original back. Now, I could admit that that's going to be a little bit more difficult for you if you've not had a lot of practice in doing that. So maybe there's an easier way of doing it, but that's the way that I did it. Again, you might find it useful to make the model, all right, if you need to. So then I can look at this one. For this one, because it's symmetrical, you can see that if I put take the plane that the plane that the phosphoruses are in, and I put a mirror down there, the hydrogen's on this side, the hydrogen's on this side, and it goes through the CO anyway. So that is also not going to have an enantiomer. You could apply the same. You can sort of make the mirror image in your head and then see that it won't give you a different compound. I'm just trying to think if there's any tricks that you can use. I'm sure there is. It's been a long time since I did this properly. You know, I'm sure someone that does this on a day-to-day basis would know that there's like a trick that you can say, well, like if I swap any two non-opposite groups, do I get the same one back? But it's not. I can't think at the moment. And then this one, again, it should also be clear that that one is not going to have an enantiomer either. I'm just thinking, because I did do this question in preparation, and I think I did it slightly differently. I think you could ask yourself the question, okay, well look, is there any other way of having the 3 PPH3s in a plane and the 2 hydrogens adjacent that isn't the same as this? And there isn't. And you ask the same question here. Is there, because obviously if it's an enantiomer, it must all be connected in the same way. So it must have the PPH3s in the plane and it must have the 2 hydrogens opposite each other. So is there another way that has those features, that has the 3 PPH3s in a plane, has the 2 hydrogens opposite each other, but isn't this molecule? And it should be clear that that's not possible, so that can't have an enantiomer. And then we can ask ourselves the same question again. Can I have the 3 PPH3s on the same face and then make another molecule, a different molecule, where the hydrogens and the CO take the other spaces? And it should be clear again that it's not possible to do that. So there is, I guess, that way of doing it, which doesn't need you to draw it all out or do the manipulation in your head too much. Okay, well, Anyway, let's move on. So, then we get to the fun part of the question. So, the catalyst can be analysed by this phosphorus NMR technique. It's 100% abundant. Fantastic. That means we're not going to get any confusing combinatoric situations. And it's spin half like 1H NMR. The phosphorus NMR is running in a way which means there's no coupling between 31P and 1H, which means that they're not going to split each other. Okay, so in a high resolution proton NMR spectrum you will get splitting because of adjacent protons, but here you're not going to get splitting due to these two being next to each other. The only coupling which is observed is between phosphorus nuclei in different environments. Fine. What is observed in the phosphorus NMR spectrum of this catalyst? So we go, we look at our three phosphoruses, phosphorus, 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 and we decide, are they in the same environment or are they in different environments? Well, it should be clear that this one is definitely in its own environment. Let's call that PA. And that's because this phosphorus is opposite hydrogen, whereas these two phosphoruses are opposite each other. Okay? And then we decide, are these the same or are they different? Well, they're opposite each other, and they've got a hydrogen, this has got a hydrogen and a hydrogen, this has got a CO, this has got a CO, and then they've both got this final phosphorus. So, in other words, there's a plane of symmetry that runs through the centre of the molecule opposite these two, which means that they must be the same. So this one is split by 2, which gives me a triplet, and then this one is split by this one, which gives me a doublet. So I would expect to see one triplet and one doublet. Okay, so this one here, that gives me the triplet, and then this one here, that gives me the doublet. Then this is like one of the all-time greats. This is such a fantastic question. And how many marks is it worth? It's worth 3 marks. Okay. The proton NMR spectrum. The 2 hydrides appear at negative chemical shifts. So I've got, and for this question, you've really got to understand what it's asking you. So I've got the 2 hydrogens here. Okay, and it says they've got complex coupling patterns. Here they are. So one of these is due to one of these, and the other one is due to the other one. The couplings observed for these signals arise from coupling through 2 bonds to either 1H or 31P, and are measured in hertz. So in other words, when you get a split, so if I have a signal in a low resolution NMR, but then when I do the high resolution, you find out that actually it splits into a doublet. What we have is the coupling constant is this to do with the size of the gap between the 2 signals that you have, and it's measured in hertz. Okay, so the coupling constant between 2 nuclei that are trans is usually larger than between 2 nuclei that are cis. Fine. Okay, the signal at minus 6.83, this one here, is a triplet of doublet of doublets. The signal is split into a triplet with a constant of 31, then into a doublet with a constant of 15, and then a doublet of 6. And then it says the one at minus 8.8, this one here, is a doublet of triplet of doublets. So it's a doublet with 74, then a triplet with 28, and then a doublet with 6. And it says complete the table. So I've got this table here, and it wants the constant for each of those. So what is happening here? If I've got hydrogen J and hydrogen K, HJ and HK, it wants to know what's the coupling constant between those 2. So it's important for us to realise that I've been given these numbers. So I've got 31, 15, 6, 74, 28 and 6. So all of these here is going to be one of these, and I will have to use all of them, but some of them I will need to use twice. Okay, so let's think. what is my first piece of information that I can use? Well, I was told that the coupling constant between two nuclei that are trans is usually larger than between two nuclei that are cis. Now there is only one trans coupling, and that is HK and PY. So those are the only two that are trans. Now at this point it's very easy to get confused and think to yourself, well hold on, what about PW and PX? Those are trans as well. But remember, we are, even though phosphorus has a spin half, we are doing the proton NMR spectrum. Okay, so it stands to reason that because we are told up here that the coupling constant between two nuclei that are trans is usually larger than between two nuclei that are cis, we can assume that HK and PY is going to be our largest coupling constant, 74. So I'm going to go in here, I'm going to put HK, PY is 74. Okay, then so what's happening? Let's just take stock and make sure we understand. So this hydrogen here is being split 3 times. It's being split once by this one, once by this one, and then once by these because they're in the same environment. Okay, and then likewise this hydrogen here is being split once by this one, once by this one, and then once by these two that are in the same environment. Okay, so that's why you actually get 3 things. You get the triplet, doublet, doublet, or the doublet, triplet, doublet. Okay, because there are 3 splittings for each one. All right, so what other piece of information could we use? Well, if I split them up, this one is 31, 15, and 6, and this one is 74, 28, and 6. So we notice that in both cases there is a 6. Okay, so we have a doublet with coupling constant of 6 and a doublet with a coupling constant of 6. So what could that be? Well, the only thing that's the same for both hydrogens is the other hydrogen. So here, this hydrogen is split by this hydrogen, and here, this hydrogen is split by this hydrogen. So it would make sense that our HJHK is our 6. Okay, so now we've used up 6 as well. Okay, so next. At this point, we can realise as well that which hydrogen's which one. So we've said that the 74 is to do with this trans situation. So this paragraph here is for HK, and this paragraph here is for the other hydrogen, HJ. Okay, so for HK, I've assigned the 74. So for this hydrogen here, I've assigned the 74 being due to this one. I've assigned the 6 as being due to this one, which means that the splitting due to HK and PX must be the one remaining 28. So HK PX is 28, and PX and PW are the same, so HK PW is also 28. Okay, so now I'm done with HK. Okay, that's done. I've assigned all those. All right, which means I just need to assign 31 and 15. Okay, so how do I do that? Well, I'm told that for HJ, this is the one we're worried about now, the signal is split into a triplet with 31. Well, the triplet is going to be due to these two that are in the same environment. So HJPW, HJPX has to be 31. HJPW, HJPX is 31. And then I'm going to get a doublet due to my PY. So it says further split into a doublet of 15. That's going to be my PY. Okay. So there was a couple of little strategies there. I think the most difficult thing for this question is just working out what it's actually asking you. Because once you worked out what it's asking you, it's just a bit of sort of detective work and problem solving. But that might require another watch if it wasn't completely clear. But good luck.